So, this is the question. This is the question. This is basically the last slide we've seen on Monday. We've derived these two equations, which together are equivalent to a combination of the law of conservation of energy and the law of conservation of linear momentum applied to the elastic collision. And so, as we know, it's very important to remember the exact meaning of each variable when we write equations. So keep choosing your answers. I just want to mention another name for the elastic collision, which I actually used last time, and I usually like this using more. It stresses the fact that mechanical energy doesn't change, no friction involved at all. So this is how people name all these collisions here in the US. In Russia, that would have been the literal translation, absolutely elastic. But this word doesn't do anything mathematically. It just stresses again. Yeah. Well, the extremity of this case, we have two extreme cases, this one and this one. So it is just a name, elastic or absolutely elastic, same thing. And of course, it's a component, it can be both. So now, what do I do? Now, we're just going to use specific values given to us to solve specific problems. This is one of these specific situations. We know the mass of each cart, we know the speed of each cart, we know how they move, and all we have to calculate is the velocity of each cart after the collision, which is elastic. So this word means this, and we have proved that we can use these two equations. So we're not going to do it again and again, we're just going to use these equations. Here, what we know, well, let's call them the object number one, the object number two. So the mass number one times, well, this variable supposed to represent the x component. We say x, we draw an axis, and that should be a positive component minus, well, that's what we don't know. What's happening after the collision, that's what we're looking for. And that has to be equal to 0.4, which is the mass of the second cart, times this minus, well, this variable should represent the x component of this velocity. And that has to be a negative component because it's opposite. The magnitude of the velocity equals 2. So this is the most general case when masses are different, speeds are different. That's the first equation. The second equation, actually, let's just first simplify this equation. 2 times 2 is 4. 0.4 and minus and minus makes it plus. Now, this equation, so again, this is 2 plus u1 has to be equal to u2 plus, and as we said again, that's supposed to be a component which is negative. So what can we do now? Well, the easiest way is to add equations or subtract equations to eliminate some unknowns. But before we're doing that, we need to have the same variable in both equations, but with opposite sign. For example, if I take this equation, the equation number 1, and I divide everything by 2, what does it give me? 4 divided by 2, 2. 2 divided by 2, 1. 0.4 divided by 2, 0.2. 0.4 divided by 2, 0.2. So now I can see 2 variables, opposite, plus u1 minus u1. So if I add these equations together, what does it give me as the result of the addition? 2 plus 2 is 4, plus u1 minus u1, 0, they cancel each other out. And what's going to have to happen? So on another side, well, there is always an invisible 1, a coefficient, which we always can make visible. So 1 plus 0.2, 1.2 times u2, and negative 1 plus 0.2, negative 0.8. And now we can solve it for the velocity of the second chord after the collision. So it's going to be 4 minus 0.8 divided by 1.2, 2. The chord on the right is the second chord. So the result is positive for this velocity, which means the x component of the velocity of the second chord after the collision is positive. So that velocity u2 points to the right. So it bounces off the first chord. And we can calculate now the u1. u1 represents the velocity of the first chord after the collision. So how can we do that? We can use the equation number, well, any equation will do right now. So I'll try to fit in here. Well, I'm not going to solve it. Oh, actually, u1 will be equal to 4 minus 0.8, that's 3.2. 3.2 divided by 1.2 is 32 over 12. 32 over 12, please tell me. Yeah? Where? Where? Shoot. Of course. Thank you. Well, we have to recalculate. 4 plus 0.8, 4.8. 4.8 over 1.2, it's 48 over 12. That's 4. That's a nice number. I would expect something like that. That's an S, meters per second, not a 5. It just, every time when I try to write close to edges, there's some kind of a skewing. That's just a feature of this particular screen. So I'll try one more time. Meters over a second. That's U2, sorry. But now we can calculate U1. U1 will be equal to 4 minus 1 minus 2, 1. What does it tell us? It tells us that this cart actually slows down, but still keeps in the same direction because it's much heavier and it was traveling much faster than the first cart. We can, okay, so magnetic bumpers. Okay, this cart is broken. These wheels didn't move. Okay, moving on. Next time. I'm back. So this cart is broken. I have to. See, magnetic bumpers are practically frictionless. These wheels practically frictionless. We can neglect any friction, and it's not leveled a little bit. So. Every time I think maybe I have a power, every time I'm disappointed. So this should be much heavier, so we can add some weight to it. And let's see, this should travel fast, this should travel slow. Oops, see? Well, you get the idea, right? So even that was moving too fast, so. See? So what does it tell us? It tells us that in general we don't know what will be happening after the collision. Anything could happen. They might bounce in opposite directions, travel in the same direction. They might even stop. Oh, almost. So every time we just have to solve a problem again and again and again. Let's move on. A specific case when one cart was initially at rest and carts had the same masses. What should happen? Well, so first of all, we can cross out this term. It's 0, and that's 0. Now we can cancel masses. They actually don't matter at all because they're equal to each other. So what we have is this minus this equals this, and this plus this equals this. How can it happen? Well, you see they equal to same variable. Well, the result is, you solve it, u1 equals 0. What does it mean? It stops. But now, hence, u2 will be equal to initial velocity of the first cart. So this is a special case when people use when they play pool, for example. Make a hard shoot, the ball hits another ball, stops, and that goes in the pocket. So something like that. So, see, physics works. Of course, it has to be leveled very accurately, neglecting friction, but still. We use the same strategy again and again and again and again. So this situation describes many, many possible cases. You see, this is just a coefficient between two masses. It could have been any number, 1/3, 5, 10. I'm going to solve this for the specific number, coefficient equals to 3. But whatever steps I'm going to use will work for any number, for any relationship. Well, first of all, same speeds. Same speeds. What is the speed? what is the definition of speed? Nope. Please. So I want to show this again, so it would be on the camera. So please, definition of speed. Speed is not good enough. There is a specific definition of that physical quantity speed. I think it was lecture number 2. See? Still works. Speed? Nope. Speed? Let's keep venturing ideas. That's a good exercise. Right now, your brain, if you're trying to remember, your brain actually firing up so many neurons. So that's a good thing. So? Now that would be average speed. What is just speed? Which is a shortcut for instantaneous speed. That might help. Okay, if we relate something to a specific instant, that's what we call instantaneous. Yeah, but there's a physical quantity, we call it velocity. There's physical quantity, we call it speed. What's the difference, or what is the relationship? Exactly, that's it. That's the definition. It has to be in the memory. It has to be in a memory exactly like that. No different word. Speed is the magnitude of velocity. That's what it is. Instantaneous speed is the magnitude of instantaneous velocity. That's more accurately. So if they travel with the same speed, this information doesn't tell us anything about the direction. But well, picture shows the first velocity points to the right. Now, how should be the velocity of the second cart be directed in order to collision to happen? Exactly. Because if you travel with the same speed in the same direction, they never collide. So, in this situation, because it is a collision, V2 should point to the left. What about U1 and U2? We don't know. That's what we're looking for. So our general assumption, let's point them both to the right, and if the final calculation will give us a positive value, that means they do indeed point to the right. But if the final calculation leads to a negative value, that means the actual direction will be to the left, will be opposite to the chosen one. Okay. And you should start writing, because now you know what steps supposed to be done, right? So first, x times m2 should be multiplied by, what did I do? I replaced the first mass with what it's equal to, actually no. 3, yeah. I use all the information immediately. Now, because speed is the same for both, we don't need different subscripts. So let's just call it a v. That's the speed now. You see? That now, the speed, that's magnitude, that's absolute value of velocity, so it's positive automatically. Now, that's going to be v minus u1 should be equal to m2 times u2 minus. Now, that's supposed to be equal to the x component of the velocity of the second cart before the collision. And because the velocity of the second cart before the collision points to the left, the x component has to be negative. So if we knew a number, we could write -5 or -7, but we don't know the number, so we write negative v. because v is the speed, and negative v represents the component of that vector now. So v plus u1 equals u2 plus, well, again, this variable represents the x component of the velocity of the second cart before the collision, which is supposed to be negative. But my variable v represents a positive number. So this is automatically a negative number. Now we can cancel m's. So 3 times v minus 3 times u first equals u2 plus v. V plus u first equals u2 minus v. Now, what do I want to do? I want to eliminate one of the unknowns as soon as possible. And here, the fastest way would be subtracting those equations. Because in that case, u2 minus u2 gives 0. They would cancel. So I'm subtracting. So 3v minus v, 2v. Negative 3u1 minus u1, negative 4u1 should be equal to 0. And v minus negative v, 2v. What does it tell us? That we can cross them out, and in this situation, u1 has to be equal to 0, which means the first cart should stop. This is only because of this specific number I've chosen. But if the number would be less, like 2, that would mean that cart actually should bounce back. But if the number would be 4, that would mean that the first car would slow down, but would be still moving in the same direction. So that's a critical number for what might happen. Well, the only thing is, let's try. The only thing is they must travel with the same speeds initially. So this is about 250 grams. 250 grams. And that should be now 3 times heavier than this one. The only thing is they should travel with the same velocity. Well, close enough. So if I add some mass, what should happen? Again, with the same velocity. Still keeps traveling slower, yeah? But if I make it lighter, see, physics works. No magic. And of course, we can calculate now the velocity of the second cart after the collision. That should be equal to this, right? Because this becomes equal to 0. So it was negative, now it's positive. So now it travels to the right. Any questions? All right. Not all collisions are like that. Not all collisions are extreme. Yeah. So this could have been happening. So of course, we should draw a picture now, before and after. This picture is before. What's after? After the collision, the carts changed the shape. Now they oval. We don't know this velocity. And what we know is this velocity. You see, it says the cart on the right reverses its velocity but keeps its speed. So what does it tell us? That u2 supposed to be directed to the right, and the magnitude of the U2 should be equal to 1. Because it was 1 before, so we just read the text and we translate it into the information we're going to use. Well, this is plus 1 now, because positive x direction points to the right and U2 points to the right and the magnitude is 1. So now everything is clear. Now, my question to everyone: can we use equations and of course we have only two answers, yes, no, I don't know. We if we answer no, or if we're not sure, we don't know, that means we can't. Yeah. So in that case, what do we do? In that case, we should start from the beginning, from the original equations. And the original equation is the law of conservation of linear momentum first. And let's see what it gives us. This component is supposed to be negative, but we are told that component is supposed to be positive. So that's not 2.2, that's 2 times 2, right? So 2 times 2 is 4, 4 minus 0.4 is 3.6, that's a point. And that should be equal to 2 times this plus 0.4. So 3.2 divided by 2 should be equal to this, which gives us 1.6. No, we cannot. Write it down. Today, I was wrong. Again, that helps your brain to not repeat the same mistake next time. That's just a pure psychology, nothing special about that. Pure psychology. Why you don't move? All right. These equations can be used only when we know for sure there is no friction. Only when we know, absolutely sure, there is no friction. In this situation, we're just not sure, we don't know. That's part of the question. So, no, we can't. We have to do the original work, calculate the velocity first, which we did, and then we can calculate if kinetic energy actually changes or not. And how would we do that? Well, the change in the kinetic energy is equal to m1u1 squared over 2 plus m2u2 squared over 2 minus m1v1 squared over 2 plus m2v2 squared over 2, because that's what it is. We have only 3 options. It's positive, it's zero, it's negative. Nothing else can be happening. If it's positive, what does it mean? It gained energy. How can it happen? That's super elastic collision. During the collision, some additional like explosion might happen. That's it. If it's zero, no friction has been involved, that's the elastic collision, or Russian way, absolutely elastic collision. If it's negative, that means mechanical energy decreased, some friction had been involved, so that's elastic collision, just what we call elastic. Inelastic collision. Inelastic, elastic, super elastic. So now we know all the numbers, so we can just calculate the numbers and see what's happening. If I remember correctly, it was a regular inelastic collision. Some energy was lost. Now, another example. This is a problem which combines all our previous knowledge. First of all, we have to consider stages. It happens in stages. So I'm going to start asking you this question. This can be closed. This is open. So what stages should we consider? Well, first of all, the stage number one. Oops, go back. Stage number one. This ball is moving down. That's a ball on a string moving down. We've said everything about the situation before. If we neglect the air friction, we can apply the law of conservation mechanical energy. So mgh initial should be equal to mv squared final. And of course, we set the final, the lowest position to 0. So that's it. That's the first stage. Has nothing to do to collision yet. But when does collision start happening? When the second ball and the first ball now start touching each other. So that's the collision. And for this situation, in general, how many equations can we write now? 2, right? We can write the law of conservation of linear momentum, and we can write the law of conservation of mechanical energy, or work kinetic energy theorem, or master equation, same things. And in general, again, we have a fork here. We are told clearly, specifically, that there is no friction. In that case, we can use those equations, yeah, 2 equations we've derived. Or we don't know. We're not sure if friction is involved, or we specifically told there is some friction. In that case, we just have to use these equations. Law of conservation of linear momentum, law of conservation of mechanical energy. So after that, what's happening? Well, in general, again, we know they might travel differently. Now, why is 37? It's supposed to be 70. It's like 78, 79. Why 38, 39? I'm going to stop collecting in several seconds. So please press. Now, so after the collision, let's say, come back. Okay, it's in a movie. That was stage number 1, stage number 2. Now what's happening? Let's say they move in opposite directions. So in that case, they both eventually stop somewhere, height number 1 or height A, height number 2 or height B. And for this process, again, we just apply the same law of conservation of mechanical energy again, because if we know the speed, they starting moving away from each other. We know kinetic energy eventually getting transferred to the potential. It stops instantaneously. What's happening after that, we don't care. Problem solved, done. So, of course, I've got some general equations which describe all these stages, but we're going to solve one specific example soon. Here, these equations cover all possible situations. So if we're not sure if friction is involved, we should keep this term, just in case. If we are clearly told there is no friction, we can cross it out, non-conservative forces. Well, I said that, two cases, 0 or not 0. And we're going to solve a case with 0. Let's see what you said. Well, that's not a tricky question. Of course, what we saw is just exactly the same case of two carts colliding. One was initially at rest, and another was hitting that cart. So right, left, left. This is at rest, and this is moving. We can't say what might happen to this cart because it depends on the ratio between the masses. But definitely, if it's not moving now, after the collision, it can't go that way. It just has to go that way, not tricks. So no tricks at all here. This is a specific case I want to solve. Collision be elastic, or we know another outdated term, absolutely elastic, and the mass is, well, quadruple. Because of this word, we can use those equations. So let's use them. That saves time and effort. Well, let's call them A, B, 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 A, B, B. So, first stage, the ball falls down. We measure its height from the lowest position. So, mgh will be equal to ma va squared over 2. V is equal to square root of 2 times 10 times 0.8, 4. So now the most important part of this problem is the collision. That's our current topic. This picture shows the situation before the collision. VB equals 0, and VA equals -4. VA represents the component relative to this axis. And at the bottom, it moves to the left, VA. So, and again, even if it physically doesn't make any sense, we still can make an assumption that after the collision, immediately after the collision, they both travel to the right. We can make this UB and this UA directed to the right. Of course, when we solve it, UB must be equal to a certain negative number. And if that is indeed going to be a negative number, well, good, everything worked. So, MA times -4 4 minus first velocity after the collision should be equal to 4 times ma times u2 minus 0. And if we cancel masses, our equation looks simpler. Negative 4 minus u1 should be equal to 4u2. The second equation. Negative 4 plus u1 should be equal to u2 plus 0. And, well, probably fastest way, just add them up. Negative 4 and negative 4 is negative 8. Minus u1 plus u1 is 0. And here we get 5 times u2. So u2 should be, which is ub, the same thing, should be negative. So, which is consistent with my weird assumption. I thought it could have been moving to the right, and it gave me the negative result. So in actuality, of course, that ball, as we said, will be moving to the left. And I'm going to move on, because the rest is exactly the same sequence of steps we've just done before several times. Two-dimensional. Again, it doesn't matter if we have an explosion or two objects collide and then travel together. In two-dimensional situation, the law of conservation of linear momentum will tell us the answer. So first of all, we have two options. We can use components or we can use triangles. From a mathematical point of view, there is no difference between using three momenta or three forces. If you remember the lab with three springs or a problem with the light, three forces, yeah? Now here we have three momenta. It doesn't matter if we have to use three letters F or three letters P. Mathematics doesn't change. So we always can choose two axes, x and y, and write components relative to those axes. Or we can draw a triangle. This is the law of conservation of linear momentum. We can write it like this. Now it's just a copy of the condition for the force equilibrium. One vector plus another equals 0. So it gives us a triangle, and we can use sine law, cosine law, or if we're still not comfortable with triangles like that, we can use components, which literally means just, for example, draw a perpendicular and choose these as x and y axes. Exactly like we did before. Yeah, we use one arrow, any arrow, as one axis. We point another axis perpendicular to the first, done. And I'm going to do a specific example. So two pucks collide. Well, this is heavier, twice heavier than this one. And we are looking for this velocity. Velocity means speed and direction. So the law of conservation of linear momentum tells us that m times 1 meters per second, pointing to the right, that's p1 initial. And again, don't be confused with many, many m's. That's meters per second. This is the mass of the little puck, plus this arrow, which represents the initial momentum of the second object before the collision. And it's supposed to be equal to big M times 2 meters per second. And that has to be equal to what? That has to be equal to this arrow, which is supposed to be equal to, see, they travel together, little m plus big M, total mass, times final velocity. That's what the final momentum of the system should be equal to. And why? We can make them equal to each other because of the law of conservation of the linear momentum. That's it. Well, so m times 1 plus 2 times m times 2 should be equal to m plus 2m times this. This is a number times an arrow. That's what it literally is. So, hence, m times 1 plus 4 times m, oops, sorry, wrong direction, should be equal to 3 times m times arrow. M, that's the mass, that's a variable, common factor. What can we do? We can divide everything by m. M getting canceled. So now I gotta switch to a different slide. So I gotta test my short memory. If I cancel m, what I have left is 1 directed to the right plus 4 directing down should be equal to 3, well, it's clearer. Well, that's what we're looking for. So divided by everything divided by 3. 1/3 times that arrow plus 4/3 times this arrow should be equal to this arrow. So this is my triangle. This plus this equals that. That equals 1/3. This equals 4/3. How do we calculate the magnitude? That's the final speed, supposed to be equal to square root of 1/3 squared plus 4/3 squared, square root of 17 divided by 9 square root of 9, which is 3. What about direction? Well, we can calculate any angle. For example, this angle. The tangent of this angle should be equal to opposite over adjacent, 4/3 over 1/3, 4. Of course, you don't have to do it that way. I don't want to, deny you an opportunity to use component method and triangle method at home. So that's why I left it for you. Any questions? I think that's last example related to this topic. Then we're going to move on Friday, on the center of mass and rotational motion. So this is a very typical problem when we are given a graph for the x component of the force as a function of time. So we can imagine a cart and a person acting on this cart. The force increases, then drops to a new value, and the force remains constant. Then the force decreases in magnitude, so we speed it up, slowing down, whatever, doesn't matter. Clearly, we cannot use Newton's second law in the form m times a equals f, because we don't know how to deal with changing forces. But now we know that there is another way to apply the Newton's second law in the form of impulse momentum theorem. The impulse of the force should be equal to the change in the momentum. This is supposed to be equal to the area covered by the graph, and that should be equal to final momentum minus initial momentum. Just a second. And this is your area, green one. and final momentum will be equal to the initial plus area, and the result equals this. You may want to refresh how to calculate the area of a triangle or a trapezoid or rectangle. That's it. Thank you. I have to apologize. I didn't pass the sign-in sheet, but it's here. So please sign in. Yes, labs on a regular schedule this week. Well, all labs are according to the schedule. Someone should have reminded me. One of the longest lines I've seen. It's even shorter in the morning in Dunkin' Donuts. Yeah, but I don't know who you are. Next time I've got an assignment for you. Next time I forget to pass it. Go get it. Just tell me. Did you forget to pass it? Sure. No, I just didn't pass it. You didn't start the procedure. That's it. I just forgot. We're on a track. Okay, thank you.
No.
One died. Well, one died. One's still alive.
Oh.